because my reference, my presentation is based on two different papers, so my topic is set by myself is analysis of CMA and MPA decoder. This is the base outline. And to meet the challenging requirement of the next generation wireless communication, such as low latency, massive connectivity, and high spectrum efficiency, the innovative concept of non-orthogonal multiple access has been proposed. And as the figure below is the example of different types of multiple access. And today we are talking about the codomain multiple access is the non-orthogonal multiple access because a user will occupy the multiple users will not occupy the same frequency and time resources. And sparse code multiple access is our topic today. And because it needs to be decoded by the MPA method. And let's talk about system model. J users will group to perform SCMA techniques, especially the SCMA scheme with K resource element can support J users simultaneously, leading to an overload factor. And the H is the effect channel matrix for the J user. And let's see the figure of the system model. It implies that different users will use their own encoder to get the encoded code and sum together and transmit through the channel. And on the receiver side, the MPA decoder will help to decode the channel code for each user. And this is the concept of SCMA. It's like each block here is represent the block code book for each user, and different color represent the different constellation points. And if the user 1 choose 0, 0, and user 2 choose 1, 0, etc., and the final code of the resource element will be summed up and just like this. And this is the SCMA codebook design. Despite it's not the same as the traditional quant constellation. The constellation points of each SCMA user will generated by based on mother code. Just focus on the red block here. These 8 points represent the different constellation points of end user, and we use some constellation operator to rotate the mother code to get the constellation points of the specific user. For example, if we the mother code is this, and if we multiply the mother code by this operator, and we will get that the user constellation point of over channel 1 and channel 2 will change, and same as the user 2. And because the operator is multiplied by 0 degrees, so it didn't change. And because according to the system model, we say that we will sum up the constellation points of different users over one channel. So we focus on if we focus on one channels, how many the different type of constellation points will appear over n channel? It will be 64 different kind of constellation points. And this is the MPA decoder that it will update the belief probability of different user channel code and get the result. Just like this one. If we use the MPA decoder, we will, if we want to update the belief probability over user 3, so that we use the user 1 and according to this vector graph, we use channel 1 and channel 2's information to update user 3's belief probability. And if we want to update the second resource element belief probability, we use this resource element and this channel to update. And finally, if we want to terminate the iteration of MPA, we just set the number of iterations and we get the result of product of the prior probability and message from the neighboring fn's of each bn. And we further make the selection of the final bits through this LLR equation. And this is my simulation result. As you can see, if my information bits generated by random, and you will get this 12 bits. And after I encode it by my code book, it will be the red point. It's the constellation plot. Constellation plot, yes. And because I add some noise to simulate the transmission, so the blue one is the channel code that is added by noise. And the decoded and the receiver side, I decode the channel code by the MPA decoder, and I get the same bits as the general the information bit I generated. And because this is the I done this simulation under the fixed SNR. So if I do this decoding through different SNR, it will be this trait. But this trait is not as the same as the paper of the result of the reference I think. And I guess because I do the MPA decoder by myself, so maybe there are some parameters it's not the same as the paper, so I will fix it. Yes. Thank you very much.
So of course you should follow as possible as you can.
Yes.
And also I have a question.
Yes.
About the simulation. Do you have any random phenomenon included in the simulation? You have noise, right?
Yes.
So you should have the random phenomenon. I'm not sure, so that's why I mentioned this.
Okay.
Yeah, because we have the random number generation, so of course you need to include at least random number.
My noise I generated is the complex Gaussian noise.
Oh, sure. Gaussian is normal.
Yeah.
Okay. All right, that's it. So at least you need to check it further.
Yeah.
Okay, that's it. Thank you.